The purpose of this lab is to observe and analyze the motion of a falling object, then create a model representation of the motion and apply physics principles of gravity and drag force to improve the accuracy of the model. The results of this experiment show that the original model prediction, where only gravity was included in the net force, consistently overshot the change in velocity compared to the experimental data. By adding an additional force, we were able to make our data much more accurate and consistent with our experimental data. More on this later. Let's look at the experiment setup and the data collected. The experiment uses a couch pillow held at rest, then dropped along the negative y-axis. The video is calibrated to be in meters per second. We stopped this video right before the pillow hit the ground in order to ensure the only forces acting on the pillow were drag and gravity. Because the pillow rotated, the axis had to be tilted slightly to keep our system's center of mass along the y-axis. When we analyze our data, we can see that the velocity is not constant and is changing. When we look at Newton's second law, we can see that this change in velocity is due to the net forces acting on the object, which must be non-zero. We can observe the force of gravity on this object using a weight vector. This is equal to the object's mass times Earth's gravitational constant. This equation is then used in our model to calculate the weight force for our system. In the first model, the gravitational force was the only force studied, so the net force was equal to the gravitational force. Newton's second law is then applied to our loop with the new net force accounted for in order to calculate new velocities and positions over time. When we compare our results, we can see that the slope of the model is much steeper than the experimental data. This means that our model is falling at a much faster pace than the experiment. If we go back to Newton's second law, we can see that we need to do something to change the net force in order to decrease this change in velocity. We can also see that if we're adding a vector, it needs to be in the negative direction in order to decrease the total value for Fnet. The drag force is sometimes referred to as air resistance. It acts in a direction opposite of the system's motion. Drag force can be related to the system using the equation below, where B is a constant. For our model, we found that the most accurate data could be found when B was a value of 2. The drag force was then added into our net force value, and the velocity and position loops were recalculated. We can now see that our new data is much more accurate with the added drag force. We use an alternative equation to account for drag force, shown in this slide, where we use the velocity of the motion squared. It still is acting in the opposite direction as the velocity. However, it's just a little bit more accurate when you look at our experimental data. Possible errors for this experiment include guessing the weight of the pillow using online comparisons, the rotation of the pillow, which could affect the constant B, because the rotation in the pillow would cause changing shape and amount of surface area affected by drag. The center of mass was also possibly inaccurate because the speed of the falling object created a blurred vision, and the center had to be guessed. We were asked if either model reaches a terminal velocity. This is found when the system reaches a point where the forces acting on it balance out, and therefore the object reaches a constant change in velocity. The models where drag force is accounted for will reach terminal velocity over time because they will balance out the gravitational force until the net force is 0 and cause the object to move at constant velocity. You can see this in the plots where the drag model and the experimental data over time become more linear. Our what-if problem addresses what would happen if the object had been thrown down instead of falling from a stop. This implies that the initial velocity would not be equal to 0 when the object is thrown down. This actually happens to be a condition that I already had for my experiment because I started tracking my data a little too late. So I reversed the problem to compare what the change in velocity would look like if the system had started from rest. The graph on the right shows the comparison of the two, and shows that the terminal velocity would be the same for each scenario. The initial velocity does not affect the gravitational force because the same amount of drag force is needed to balance out the gravitational force either way. In conclusion, we find that when an object is moving at non-constant velocity, there must be one or more forces acting upon it. The drag force is usually present and always acts in the opposite direction of motion. It needs to be accounted for. In the case of a falling object, the drag force will even out with the gravitational force in equal and opposite direction to reach terminal velocity. If given enough time, terminal velocity will be constant for an object despite its initial velocity conditions.